Now we're going to go ahead and look at our solutions unit and the various aspects of solution processes. By the end of the video lecture, you guys should be able to differentiate between solute and solvent. You're going to be able to describe the solution process in specific terms. You're going to be able to tell me the difference between non-weak and strong electrolytes. You'll tell me how attractive forces between solutes and solvents affect solution production. And you guys are going to describe the difference between types of saturation. And you're going to utilize the solubility curves to tell me how much of a solute is dissolved in a specific value of solvent. So a solution is a homogeneous mixture that consists of a solvent and a solute. We've discussed homogeneous mixtures. They are mixtures that are uniform throughout and have such small particulate that light can pass through these solutions. So now that we've had a little review on that, let's go ahead and let's talk about the new terms, which are solute and solvent. So the solute is the substance that's being dissolved, and the solvent is the substance that is actually doing the dissolving, and it's generally present in a greater quantity. So an excellent example of a solution being made with a solute and solvent is something like Kool-Aid. You get the powdered package of Kool-Aid, which is your solute. You add it to a large quantity of water, which is your solvent. You mix together and you have a delicious drink. Okay, so that is a solution that you guys are probably familiar with and may have created on your own. Okay, so if we look at this nice little diagram here, you guys will see that we have this pinkish stuff, pinkish purplish stuff, and that's potassium permanganate. It's a solid ionic compound that has been added to a beaker containing water. Now, as you can see, this solid is starting to disperse throughout the solvent. Okay, and so the solution process is driven by the interactions between the solute and the solvent. And those interactions are going to be what allows the solute to disperse throughout the solvent. Now, this process of creating a solution or dissolving a solute in a solvent is known as solvation. Okay, and the process involves basically two main steps. The first thing that happens is the solute particles are surrounded by solvent particles. So if we go ahead and we draw a little diagram, what we'll have in this diagram is basically our solute particles. They're all interacting with one another, and they get surrounded by our solvent particles. And basically, as the interactions between our solvent and our solute start to become more intense, what ends up happening is that the solute particles become separated from the original block or the original grouping of the solute particles. And that would look something like this. And as we can see in the diagram here, basically the previously clustered solute particles are now completely surrounded by the solvent particles. And what happens is this is what allows the solute to be dispersed evenly into the solution. Now, a couple things we need to talk about are really what are we dealing with here in terms of the interactions. Okay, so the interactions that we're talking about here are IMFs. Remember, intermolecular forces. We have our London dispersion forces. We have our dipole-dipole. We have our hydrogen bonding. And of course, we have our ion-dipole interactions. Okay, and basically what we're doing is we are overcoming intermolecular forces between the solute and creating new ones between the solute and the solvent. And depending on the relative attractive forces and the degree to which those IMFs match, that's going to dictate the solution process. So solvation is going to be broken down into various subcategories. And these subcategories are going to be dictated by the types of solute and solvent that are present. So in dissociation, we're going to be dealing with ionic solids that are dissolved in polar solvents. And the most commonly used polar solvent is going to be water, which is why in this particular case, we're going to be referring to the ions in solution as aqueous ions. So as we can see here, we have our ions in our ionic substances lattice. Notice there's a repeating positive, negative throughout the structure. And basically what's going to happen is, once again, this is going to be surrounded by our water molecules, kind of like what we see here. And then each individual ion is going to be isolated and subsequently dissolved in the water molecules. Now, we know that the water molecules that we've looked at in the past are in fact polar molecules. If you recall, this is our structure. And remember that there's a partial negative and partial positive regions of the molecule itself. Okay, and that's going to dictate the directionality of the interaction between the water molecules and the ions that are isolated. Okay, so obviously the negative, partially negatively charged region of the water molecule is going to want to interact with the positively charged ion. And of course, the positively charged region of the water is going to want to interact with the negatively region of the solute. So what's going to happen here is we're going to have basically our solute get surrounded by our water molecules, which are our solvents. And as you can see here, this looks very much like what we discussed in our previous slide. Okay, so basically you have your solvent surrounding your solute. And then what's going to end up happening is the ions are going to get isolated out. And that's going to look something like this. Go ahead and take a look here. Notice that the sodium ion is interacting with the negatively charged portion of the water molecule, while the chloride ion is interacting with the positively charged portion of the water molecule. So basically what we've done is we've overcome the attractive forces between the sodium and chloride ions, and the water molecules are now interacting with these individual ions in an ion dipole type of interaction. Okay, so this is dissociation. Basically, you've taken your ions, dissolved them in water. Now, in terms of indicating this process in reaction equations and things like that, notice that our chloride ion is represented as AQ and our sodium ion is represented as AQ as well. That is referring to the surrounding of those ions with the water molecule in the solution process. So the next process we're going to be talking about is ionization. So basically this solvation process involves polar molecules instead of ionic compounds interacting with the solvent to produce ions in solution. Okay, so instead of having an ionic compound here, we have obviously a polar covalent substance that gets subsequently broken into its ion pieces. Now, we'll talk about this in great detail when we discuss acid and base chemistry, but basically what we're dealing with here is very similar to the previous example. Water molecules are going to surround the polar molecule and subsequently isolate out the ions. Now, there's a little bit more bond breaking and formation that happens in this particular type of situation. But again, we'll discuss that in our acid and base chemistry unit. Now, the last example here of solvation is molecular solvation. Okay, so in this situation, guys, the molecules stay intact. Okay, so what do I mean by that? Basically, if I take a sugar molecule and I put it in water, that sugar molecule, all of the bonds are going to stay connected. The molecule itself is not going to change. The only thing that's going to happen is that the individual sugar molecules just get surrounded by the water molecules. And basically, in this particular situation, you have no ions. Okay, and this will be important later, but molecular solvation is typically going to occur with nonpolar covalent compounds. And these compounds are going to, of course, dissolve, just like the other examples that we saw, except that we won't have any charged species in solution. So the presence of ions, or lack thereof, is going to be what helps us determine whether our solute will behave as a non-weak or strong electrolyte in solution. And what we have here, guys, is basically we have an electrical current that's being run through our various solutions. So we have a solution that contains sugar and water, one that has acetic acid and water, and one that has something like sodium chloride. So basically what we have here is molecular solvation, ionization, and dissociation. Okay, and so the quantity of ions present in each of these solutions is going to increase as we go from left to right here. Okay, so if you look at this, if you notice this sugar solution, when the electrical current is ran through that solution, the bulb doesn't light up. We'll come over here to the acetic acid, or the polar covalent molecule solution. We have a very faint glow, so some electrical current is able to travel through because there are ions present. And when we look at our salt solution, we know that the dissociation of those ions is complete. So there's a lot of positively negative and negatively charged ions present in solution. So the electrical current is able to run through the solution pretty well, and you subsequently get a stronger bulb lighting than in the other examples. So if we look at these situations, the presence of a strong electrolyte is going to be something that dissolves and produces lots of ions in solution. A weak electrolyte is going to have some species that are in solution as ions and some that aren't. And in the non-electrolyte solution, there will be no ions present from the solute particles. So basically, this is how we differentiate between non-weak and strong electrolytes. So when they're talking about, hey, your Powerade drink or your Gatorade drink has electrolytes, really what they're referring to is the addition of some salt, usually like sodium chloride or potassium chloride. And basically those just help replace some of the things we lose when we sweat. So solvation can be summed up kind of simply with the concept of like dissolves like. And basically what like dissolves like is a simplification of the attractive forces, or those intermolecular forces that we've been discussing. So the idea behind like dissolves likes is that solutes with similar structural characteristics are going to want to dissolve in solvents with other similar characteristics. So the idea that if I have two polar molecules, they're most likely to have the similar types of intermolecular forces, which is subsequently going to lead to solution process. So this is why something like sodium chloride dissolves in water, because the sodium ions or the chloride ions are going to be able to easily interact with the positive and negatively charged regions of the water molecule. Okay, and with that same concept, that's why when you put oil and water together, they don't want to mix. Why? Because LDFs are the primary intermolecular force in oil, while water molecules interact via hydrogen bonding. So we're talking about a polar molecule trying to interact with a non-polar molecule, and that doesn't really lead to anything good. So like dissolves like, basically you want a polar and polar, or non-polar and non-polar solvent-solute situation. So now the creation of solutions is obviously a process that occurs, but something that we need to think about is solubility, okay? And solubility is basically how many grams of a solute or maximum quantity of a solute that will dissolve in a specific quantity of solvent at any specific temperature, okay? And so there's various ways to measure solubility, but basically the more soluble a solute, the more of it I would be able to add to a specific volume of my solvent. Okay, and solubility generally varies with temperature, and the charts and stuff that we're going to look at are going to be based on something called a saturated solution. So let's go ahead and let's define what we mean by saturated solution, and then we'll look at our graphs. So we have basically three solutions represented here. We have an unsaturated, a saturated, and a supersaturated solution. Okay, so basically in an unsaturated solution, we have not reached the maximum amount of solute that we can dissolve in this particular quantity of solvent. So basically, this is the point at which we still could add more of our solute. When we get to the point where we have a saturated solution, we've reached the maximum solubility, or the maximum ability to dissolve of that solvent. Okay, Okay, and then supersaturation is when you've gone beyond that. Okay, and you've added way more than the saturated point. Okay, and so you'll see this a lot. A supersaturated solution is something we would use to help us make like rock candy. We would heat up a specific amount of water and basically dump in a ton of sugar, way more than that would ever dissolve in the room temperature volume of that same amount of water, and we subsequently then allow it to cool down, and crystals will end up forming, and that's where you get your rock candy from. But basically, this is the differentiating factor, which is basically how much solute has been dissolved or attempted to be dissolved in the solvent. Now, before we go into the specifics and the use of graphs and stuff to find out our relative solubility of our solids, I do want to talk really quickly about some vocabulary. So the phrase miscible refers to basically a liquid solute that is soluble in another liquid. Okay, so something like alcohol dissolving in water, that's an example of a miscible solution. Immiscible, so like oil and water, is an example where you don't have the mixing process. Okay, so these are two vocabulary pieces that you should be familiar with because they may come up later. So now let's go ahead and move on to the solubility curve. So what is the solubility curve? Basically, the solubility curve tells you or shows you the dependence of the solubility of a solute on temperature. So if we look down here, notice we have temperature values, and here we have basically the relationship between our grams of solute and our quantity of solvent. Okay, now guys, I need you to always come and look at this value right here. This value can totally change. This could be out of 200 grams or 500 grams of water. Please make sure that you're familiar with that. Okay, so if we look along our y-axis here, notice we also have numerical values. Those numerical values are going to be basically referenced relative to the extrapolations on the various curves that we have. And that's going to allow us to tell us how much of that solute would dissolve in that quantity of solvent at that specific temperature. Yeah, so let's go ahead and apply this. So the first question here is, what is the solubility of sodium nitrate at 80 degrees C? Okay, so how would we approach that? First thing we're going to do is we're going to come over here to our temperature values on our x-axis. And then what we're going to do is we're going to find the sodium nitrate curve. Okay, so sodium nitrate is here. That's referring to this line. Okay, and what we'll do, guys, is we'll come up from the 80 and go all the way up to being directly on the curve. Now, when I am on this curve, that is when I am at my saturation point. So at that temperature, the saturation point of sodium nitrate to make a saturated solution is going to be the value that I extrapolate over here when I move to the y-axis. Okay, so all right, so I don't know, approximately maybe like 140, something like that. So I would say I would have 140 grams of NaNO3 for every 100 grams of H2O. Okay, now we know that the density of water is 1 gram of H2O for every 1 milliliter of volume. And so we really know that this is 140 grams dissolved in 100 milliliters of H2O. Okay, but they're asking for the solubility here, and that's how we approach these problems. Basically, you find what pieces are on the graph and you extrapolate out. Now, the next question here asks you, at what temperature does potassium nitrate have a solubility of 100 grams of KNO3 per 100 grams of H2O? Okay, so what we're going to go ahead and do is we're going to find our potassium nitrate curve. Okay, and basically find the 100 gram mark, because that's what it's asking for. Then what we're going to do is we're going to extrapolate over, boom. Okay, we find that curve. That point at the curve is when I've created a saturated solution. Okay, and then I'm going to extrapolate down to the temperature axis, and basically, I don't know, approximately 58 degrees C is when that happens. Another way questions can be asked using the solubility curves are basically regarding the relative saturation or unsaturation of the solution. So in this problem, they've told us that at 20 degrees C, a solution of sodium nitrate contains 120 grams of that solid. Is the solution saturated, unsaturated, or supersaturated? So what I would do, would come over to the 20, and I would go ahead and work my way up to the sodium nitrate curve. This is sodium nitrate here, so make my way up. Boom. Okay. So I'm on the curve, so remember that's saturated. Okay. So that's about 85 grams per 100 grams, but they're telling me that they have dissolved 100, or at least tried to dissolve 120 grams of sodium nitrate at that temperature value. So if 85 is the saturated point, greater than 85 is going to be supersaturated. Okay, so basically if your quantity is above the point on the line, that is the saturation point, you're going to be supersaturated. If you're below that point on the line, you're going to be unsaturated. So that's just how we're going to approach these types of problems. You read what you need from the curves, and you subsequently approach it from there. So solubility, so far, the way we've discussed it is basically relative to solids and liquids. And we have a very intuitive sense, I think, of what solids and liquids do relative to temperature values. So basically solids and liquids, when you put them in a hotter solvent, they're going to be more soluble, right? So the higher your temperatures, the more soluble your solutes are going to be. And we see this and experience this intuitively when we, make tea. So if we make hot tea and we make iced tea, you can dissolve a whole bunch more sugar in hot tea than you can in a much larger quantity of iced tea. Why? Because that additional temperature allows those particles to distribute better in that hot tea. And so your solids and liquids, they're just going to consistently be more soluble for the most part at the higher temperatures. Now gases follow a very different path. At higher temperatures, they're going to be actually less soluble. And we experience this when we put a soda on the countertop. If you pour out a soda and you leave it on the countertop, or you pour your soda out and you put it in the fridge, which one is going to be more bubbly when you come back in an hour? Well, the answer to that, of course, is the one that's been kept in the fridge. Why? Because the gases are going to be able to stay, the CO2 gas is going to be able to stay more soluble, and that fizziness is going to be present. The one that's been sitting on your countertop is going to have already started to go flat. Okay, and that has to do with temperature values. Now, pressure can also affect the solubility of the gas. So back to our soda example. When you pull a soda out of the refrigerator, at a store, you can't see that there's any bubbles or anything present. You can't even see that there's a gas present. It just looks uniform. You can't tell that there's any gases dissolved. That's because, we bottle them at high pressures, and that allows those CO2 molecules to be really soluble in the solution. Okay, now when we open up the soda container, what ends up happening is those gas particles leave because the pressure is decreased, and that's where you get the fizzy deliciousness that comes along with our sodas. Okay. Now, another thing I want to talk about really quickly is a concept called thermal pollution. So we normally think of pollution as, dumping chemicals in the water or what have you, but that's actually not what we're referring to here. Thermal pollution is basically when you increase the temperature of a body of water, and that subsequently makes the oxygen gas that is dissolved in that body of water less soluble. And so animal life that needs that oxygen to be dissolved in the water to basically be able to breathe through their gills becomes impacted. So basically higher temperatures, less solubility of the oxygen, less oxygen leads to the dying out of animals and fish. And this can be a particular problem by nuclear power plants and places where hot liquids are dumped into bodies of water. So you'll notice issues of animal die-off and things like that, where that kind of stuff is actually occurring. So thermal pollution is basically how temperature changes to bodies of water can affect gas solubilities. So this is solubility, this is solutions. Now that you guys have a good grasp on it, let's move on to the next.